As you listen to this, a spacecraft the size of a small car is hurtling through the void between stars at nearly 40,000 miles per hour. It has been traveling for nearly 5 decades. It carries a golden record containing the sounds of Earth, greetings in 55 languages, and a small American flag. But what this ancient machine discovered at the edge of our solar system has left scientists scrambling to rewrite everything we thought we knew about cosmic boundaries. Voyager 1 found a wall of fire burning at 30,000 degrees surrounding our entire solar system. A barrier so hot it should vaporize anything that touches it, yet the spacecraft passed through unharmed. What it found on the other side changes everything we thought about our place in the galaxy. If you find journeys to the edge of known space fascinating, please like and subscribe. Your support helps create more cosmic explorations like this one. Let's begin. September 5th, 1977. Cape Canaveral, Florida. The Atlantic Ocean stretches eastward under a pale morning sky. Salt air mixes with the acrid smell of rocket fuel as technicians complete their final checks. A Titan 3E Centaur rocket stands on Launch Complex 41, its white and black exterior gleaming in the early light. Strapped to its top sits a spacecraft weighing just under 2,000 pounds, smaller than a compact car, bristling with antennas and instruments that represent the cutting edge of 1970s technology. Engineers have worked for nearly a decade to build this machine. They have tested every circuit 1,000 times. They have calibrated every instrument to detect particles and fields that no human sense could perceive. They have calculated trajectories that stretch across billions of miles and decades of time, accounting for gravitational influences from planets that would not even be in the same positions when the spacecraft arrived. 16 days earlier, on August 20th, its twin had already lifted off from this same launch complex. That spacecraft was designated Voyager 2 despite launching before Voyager 1. The naming convention reflected not launch order but arrival sequence at Jupiter. Voyager 1 would take a faster trajectory, a more direct route through the outer solar system, and would arrive at the giant planet first. The names stuck, and so Voyager 2 became the spacecraft that launched first but arrived second. The window for this mission comes once every 175 years. A rare alignment of the outer planets allows a spacecraft to use the gravity of each world to sling itself toward the next, covering in 12 years what would otherwise take 30. Jupiter, Saturn, Uranus, Neptune, all lined up like cosmic stepping stones. Miss this window and humanity would have to wait until the year 2152 for another chance. The alignment was first noticed by aerospace engineer Gary Flandreau in 1965 while he was working at the Jet Propulsion Laboratory. He was tasked with plotting trajectories for a grand tour of the outer planets, and he realized that the late 1970s would offer a unique opportunity. The gravitational assists would not only save time, but also save enormous amounts of fuel, making missions possible that would otherwise be far beyond the capability of any rocket humanity could build. At 8:56 in the morning Eastern Time, the engines ignite. Fire and thunder roll across the Florida wetlands. The rocket rises on a column of flame, accelerating through the atmosphere, shedding stages as it climbs. Within minutes, the spacecraft is free of Earth's gravity, falling into an orbit around the Sun that will carry it past the gas giants and eventually, inevitably, out of the solar system entirely. The Titan 3E Centaur was one of the most powerful rockets available to NASA at the time. It stood 160 feet tall and generated over 2 million pounds of thrust at liftoff. The Centaur upper stage, with its highly efficient hydrogen-oxygen engines, provided the final push needed to send Voyager on its way to Jupiter. The spacecraft left Earth traveling at about 36,000 miles per hour relative to the Sun, but it would gain additional speed from each planetary encounter. Communicating with a spacecraft billions of miles away required extraordinary engineering. NASA's Deep Space Network, a collection of massive radio antennas in California, Spain, and Australia would track Voyager throughout its journey. The 3 sites are positioned around the globe so that at least one antenna can always see the spacecraft as Earth rotates. The largest antennas are 70 meters in diameter, enormous dishes that can pick up signals weaker than a billionth of a watt. By the time Voyager's radio signals reach Earth from interstellar space, they have spread across billions of miles, diluted to almost nothing. The signal power received by the Deep Space Network antennas is 20 billion times weaker than the power of a digital watch battery. Extracting useful data from such a faint whisper requires sophisticated signal processing and hours of careful listening. The engineers who built Voyager 1 knew they were creating something that would outlast them. They knew this machine would still be traveling through space long after everyone who worked on it had died. They knew it would carry evidence of human existence into regions of the cosmos that no human would ever visit. The spacecraft was designed for a 4-year mission to Jupiter and Saturn. No one imagined it would still be operating nearly 50 years later, so they attached a message. The golden record mounted on the side of Voyager 1 is perhaps the most ambitious attempt at communication in human history. It is a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. The committee that assembled its contents, led by astronomer Carl Sagan, faced an impossible task. How do you explain humanity to something that has never encountered humanity? How do you communicate with an intelligence that might perceive the universe in ways completely unlike our own? The committee had less than a year to complete its work. They met in Sagan's office at Cornell University, debating what should represent all of human civilization. Every choice was fraught with meaning. Every inclusion meant an exclusion. They could not include everything, so they had to decide what mattered most. They included 116 images, photographs of Earth from space, showing our planet as a blue marble suspended in darkness, diagrams of human anatomy, showing the structure of our bodies, pictures of a woman nursing an infant, representing the continuation of our species, images of a supermarket, a classroom, a highway at night, mathematical and chemical definitions that might serve as a universal language, a diagram showing the location of our solar system relative to 14 pulsars, a cosmic map that could potentially guide someone to our doorstep even millions of years in the future. The pulsar map was particularly clever. Pulsars are rapidly rotating neutron stars that emit beams of radiation like cosmic lighthouses. Each pulsar has a unique signature, a specific rotation period that can be measured with great precision. By showing the distances and directions to 14 pulsars, the map provides a way to triangulate the position of our Sun in the galaxy, even if the map is found millions of years from now. When the stars have moved and the constellations have changed, the pulsars will still be identifiable by their rotation periods. They included sounds, ocean waves crashing on a beach, recorded on the shores of the Pacific, wind in the trees, captured in a forest in upstate New York, thunder rolling across a prairie, the sound of nature's power, the calls of birds and whales, representing the other intelligent creatures that share our planet, a human heartbeat, the rhythm of life itself, a kiss, the sound of human affection, the footsteps of a child, representing the future we hope to build. They included music, Bach's Brandenburg Concerto No. 2 in F major, representing the mathematical precision of Western classical music, Beethoven's Fifth Symphony, with its famous 4-note opening that has become a symbol of fate and triumph, Mozart's Magic Flute, representing the height of operatic achievement, Chuck Berry's Johnny B. Good, representing rock and roll and the energy of American popular culture, a Navajo night chant, representing the indigenous peoples of North America, Peruvian panpipes, representing the ancient cultures of South America, a Georgian chorus, representing the harmonic traditions of Eastern Europe, 90 minutes of humanity's greatest musical achievements, selected to represent the full range of our species' creative expression. They included greetings in 55 languages, Hello from the children of planet Earth, spoken in English by a child. Peace and happiness to all, spoken in dozens of tongues. Friends of space, how are you all? Have you eaten yet? Come visit us if you have time. Each greeting was recorded by a native speaker, preserving the authentic sounds of human linguistic diversity, and they included something else. Something personal. Something that was not part of the official plan. During the creation of the Golden Record, Carl Sagan had fallen in love with one of the project's creative directors, Anne Druyan. Their relationship was new, secret, electric with possibility. They had worked together for months, debating what should represent humanity to the cosmos, and somewhere in that process, they had found each other. On the night of June 3rd, 1977, they finally confessed their feelings to each other over the phone. Anne was in New York. Carl was in Arizona. They talked for hours, overwhelmed by the realization of what they meant to each other. By the time the conversation ended, they knew they would spend the rest of their lives together. 2 days later, Anne Druyan went to a laboratory and had her brainwaves recorded. For an hour, she was connected to an electroencephalograph while she thought about what it meant to fall in love, what it felt like to be alive on Earth, what hopes she held for the future of humanity. She meditated on human history, on the wars and the triumphs, on the music and the mathematics. She thought about Carl, about the love they had discovered, about the possibility that somewhere in the cosmos, other beings might be falling in love too. Those brainwaves are encoded on the Golden Record. Somewhere in the static between the sounds of Earth and the greetings of humanity lies the electrical signature of a woman falling in love. It is perhaps the most intimate message ever sent into the cosmos. A confession of human emotion, translated into electrical impulses, pressed into gold, and launched toward the stars. Carl and Anne married in 1981. They remained together until Carl's death in 1996. Anne later said that their love story was literally written in the stars, encoded on a spacecraft that would outlast everything they had ever known. The Golden Record remains one of humanity's most poignant attempts to reach across the cosmic void. It is a message that will almost certainly never be received, a greeting that will probably never be heard, a love letter to the universe that may never find a reader. And yet its creation brought together some of the most brilliant minds of a generation, united in the belief that the attempt itself had meaning. The record is protected by an aluminum cover that provides instructions for playing it. Encoded on the cover are diagrams showing how to extract the record from its case, how to construct a stylus to play it, how to convert the encoded signals back into images and sounds. The instructions assume nothing about the recipient except intelligence and curiosity. They use the transition frequency of hydrogen, the most abundant element in the universe, as a basic unit of time, hoping that any technological civilization would recognize this fundamental constant of nature. Whether these instructions will ever be followed is unknowable. The galaxy is vast, and the chances of the record being found are infinitesimally small, but the record exists, and it carries within it the essence of who we are and what we dream. This message was designed with a humbling assumption. The Voyager spacecraft will outlast human civilization itself, long after our species has vanished from Earth, long after our cities have crumbled to dust, long after the continents have drifted into unrecognizable configurations. These two small machines will continue their silent journey through the galaxy. In 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese, 445 in the constellation Camelopardalis. It will not enter that star's solar system, but it will pass close enough that any civilization there might detect it, might send a spacecraft to intercept it, might play the Golden Record and hear the sounds of a planet that no longer exists as it once did. Around the same time, Voyager 2 will pass within 1.7 light-years of Ross 248, a dim red dwarf in the constellation Andromeda. That star is currently about 10 light-years from Earth, but it is moving toward us, and will pass within 3 light-years in about 36,000 years before receding again. Voyager 2, travelling in a different direction, will encounter it on the outbound journey. The golden records will survive for at least 1 billion years, carrying evidence that we once existed, that we looked up at the stars and wondered, that we were curious enough to send our voice into the cosmic void. The records are protected by aluminum covers that will shield them from the micrometeorites and cosmic dust that fill interstellar space. In the vacuum between stars, there is no wind, no rain, no oxidation to degrade them. They will endure. But before Voyager could carry our message to the stars, it had work to do closer to home. In March of 1979, 18 months after launch, Voyager 1 reached Jupiter. The spacecraft had travelled more than 400 million miles, using the Sun's gravity to curve its path toward the giant planet. What it found there revolutionized our understanding of the largest world in our solar system. Jupiter is massive beyond human comprehension. It contains more mass than all the other planets combined, wrapped in an atmosphere of hydrogen and helium that extends thousands of miles deep. Its magnetic field is the largest structure in the solar system, stretching millions of miles into space and trapping belts of radiation that would be lethal to any unprotected astronaut. The Great Red Spot, that hurricane 3 times the size of Earth, revealed itself to be far more complex than anyone had imagined. Voyager's cameras showed internal structures and color variations that spoke to atmospheric dynamics we are still working to understand. The storm has been raging for at least 400 years, since astronomers first observed it in the 17th century, and possibly much longer. It is a storm that could swallow our entire planet. And it has been churning for centuries. But the real surprises came from Jupiter's moons. Io, the innermost of the 4 large Galilean moons, turned out to be the most volcanically active body in the solar system. Voyager photographed active volcanic eruptions, plumes of sulfur and sulfur dioxide rising hundreds of miles above the surface. The images were stunning. No one had expected to find active volcanism anywhere beyond Earth. The discovery was made by navigation engineer Linda Morabito, who was examining images to track the positions of background stars for navigation purposes. She noticed a crescent-shaped cloud extending off the edge of Io's disk. At first, she thought it might be another moon behind Io, but further analysis revealed it was a volcanic plume, rising 260 kilometers above the surface. It was one of the most significant discoveries in the history of planetary science. The scientific implications were staggering. For decades, planetary scientists had assumed that small bodies, like moons, would be geologically dead. Their internal heat long since radiated away into space. Io proved them wrong. Here was a moon smaller than our own, yet more geologically active than Earth itself. The textbooks had to be rewritten. Voyager ultimately identified 9 active volcanic eruptions on Io during its flyby. The volcanoes were powered not by radioactive decay, as on Earth, but by tidal heating from Jupiter's immense gravitational pull. As Io orbits Jupiter, it is constantly being stretched and squeezed by gravitational forces. This flexing generates friction, which generates heat, which drives the volcanoes. It was a mechanism that no one had fully appreciated before Voyager arrived. The tidal forces from Jupiter's immense gravity constantly squeeze and stretch Io as it orbits the giant planet. These tidal forces generate enough internal heat to drive geological activity far more intense than anything on Earth. Io's surface is constantly being reshaped by lava flows and volcanic deposits. It is a world in perpetual turmoil, its surface no more than a few million years old despite being part of a solar system that is 4.5 billion years ancient. Europa, the next moon out, showed something even more intriguing. Its surface was covered in a shell of water ice, crisscrossed by dark lines and fractures that stretched for thousands of miles. The ice showed remarkably few impact craters, suggesting that the surface was young and constantly being renewed. Scientists began to suspect that beneath that ice shell lay an ocean of liquid water, kept warm by the same tidal heating that drives Io's volcanoes. an ocean larger than all of Earth's oceans combined, hidden beneath a frozen crust on a moon 500 million miles from the Sunday. The implications were staggering. Where there is liquid water, there might be life. Europa became one of the most compelling targets in the search for extraterrestrial biology. The discovery transformed our understanding of where life might exist in the universe. For decades, scientists had focused on the habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. Europa showed that liquid water could exist far outside this zone, heated not by starlight but by tidal forces. Suddenly, the potential territory for life expanded enormously. If Europa harbors life, it would have evolved in complete isolation from Earth for billions of years. It would represent a second genesis, an independent origin of life that would tell us that we are not alone in the universe, that life emerges wherever conditions permit. The discovery of even a single microbe on Europa would be the most significant scientific finding in human history. Ganymede, the largest moon in the solar system, showed a surface divided into two distinct types of terrain. Older, darker regions covered in impact craters, representing the original surface that formed billions of years ago. Younger, lighter regions marked by grooves and ridges that suggested tectonic activity. A world with its own geological history, its own processes of change and evolution. Ganymede is larger than the planet Mercury, and if it orbited the Sun directly, we would call it a planet in its own right. Callisto, the outermost Galilean moon, appeared ancient and unchanging, its surface saturated with impact craters accumulated over billions of years. A world where nothing had happened for longer than life has existed on Earth. Callisto is so far from Jupiter that it experiences minimal tidal heating, and so its surface has remained frozen and static since the early solar system. Jupiter also revealed that it possessed a ring system, far less spectacular than Saturn's famous rings. Jupiter's rings were thin, dark, and composed primarily of dust particles knocked off the planet's inner moons by meteorite impacts. But their existence had been completely unexpected. The rings were so faint that ground-based telescopes had never detected them. In November of 1980, Voyager 1 reached Saturn. The ringed planet exceeded every expectation. From Earth, Saturn's rings appear as smooth, solid structures, beautiful but simple. Voyager revealed them to be far more complex, composed of thousands upon thousands of individual ringlets, each with its own structure and dynamics. The rings are made of countless particles of ice and rock, ranging in size from tiny grains to house-sized boulders. They orbit Saturn independently, each particle on its own path, but collectively they create the illusion of solid rings. Dark gaps between the rings were maintained by the gravitational influence of small moons that acted as shepherds, their gravity sweeping clear paths through the ring material. The most famous of these gaps is the Cassini division, a dark band visible from Earth through a modest telescope. Voyager revealed that the Cassini division is not truly empty, but contains its own fainter ringlets. The gap is maintained by the gravitational resonance with the moon Mimas. Particles in the Cassini division orbit Saturn in exactly half the time it takes Mimas to complete one orbit, creating a repeating gravitational tug that eventually clears most material from this region. Voyager also discovered several new moons of Saturn, small bodies that had escaped detection from Earth. These shepherd moons, as they came to be called, play a crucial role in maintaining the sharp edges of some ring features. Their gravity acts like a cosmic broom, sweeping material into tidy lanes and preventing the rings from spreading out into a diffuse disk. The complexity of Saturn's ring system was staggering. Computer models of the time could barely begin to simulate the gravitational interactions between billions of ring particles and dozens of moons. Saturn's rings became a laboratory for understanding planetary dynamics, and they remain a subject of intense study today. Titan, Saturn's largest moon, proved to be shrouded in a thick orange haze, This nitrogen-rich atmosphere was denser than Earth's, pressing down on Titan's surface with 1.5 times the pressure of our own atmosphere at sea level. The haze prevented Voyager from photographing the surface directly, but it hinted at a complex chemistry of organic molecules that might, in some ways, resemble the conditions on early Earth before life arose. Titan was the reason Voyager 1's trajectory was bent out of the plane of the solar system. Scientists wanted a close look at this mysterious moon, with its thick atmosphere, the only moon in the solar system known to have a substantial atmosphere. The close flyby provided valuable data, but also meant that Voyager 1 could not continue to Uranus and Neptune. That task fell to Voyager 2, which flew by both ice giants in 1986 and 1989. After Saturn, Voyager 1 turned its cameras around one last time. On February 14, 1990, from a distance of about 4 billion miles, it took a series of photographs that would become known as the family portrait. 60 frames showing 6 planets, tiny specks of light against the blackness of space. Earth appeared as a pale blue dot, suspended in a sunbeam, occupying less than a single pixel. Carl Sagan, who had championed the idea of taking this photograph despite objections from some NASA engineers who considered it a waste of resources, later wrote about what it meant in his book of the same name. "Look again at that dot," he said. "That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives, the aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. The photograph was taken from so far away that Earth occupied less than a single pixel. The sunbeam in which it appears is actually an artifact of the camera, scattered light from the sun creating a streak across the image. But the effect is haunting. Our entire world, everything we have ever known, reduced to a pale blue speck in an ocean of darkness. Sagan used the image to argue for humility, for cooperation, for the recognition that we are all sharing a tiny, fragile world in a vast and indifferent cosmos. The photograph became one of the most famous images in the history of space exploration, reproduced in countless books and articles, displayed in museums and classrooms around the world. After the family portrait, Voyager 1's cameras were turned off forever. The spacecraft no longer needed to see. Its mission now was to feel, to measure, to sense the invisible particles and fields that fill the space between worlds. 5 instruments remain active on Voyager 1, each designed to study different aspects of the space environment. The magnetometer measures the strength and direction of magnetic fields. The plasma science instrument detects charged particles and measures their energies. The cosmic ray subsystem counts high-energy particles from outside the solar system. The plasma wave subsystem listens for electrical oscillations in the surrounding medium, and the low-energy charged particle instrument measures the flux of ions and electrons. These instruments were designed in the early 1970s, using technology that would seem primitive today. They have no modern computer chips, no solid-state memory, no software updates. They run on roughly 64 kilobytes of memory, less than a simple electronic greeting card, and yet they continue to function, sending back data that revolutionizes our understanding of the cosmos. For the next 14 years, Voyager 1 traveled through the outer solar system, monitoring the solar wind as it streamed past, measuring the magnetic field that pervades our cosmic neighborhood. The data it sent back was steady, predictable, unremarkable. The spacecraft was in a region of space that scientists thought they understood. Then, in December of 2004, at a distance of 94 astronomical units from the Sun, something changed. The solar wind, which had been flowing past the spacecraft at speeds of roughly 1,000,000 miles per hour, suddenly slowed down. The magnetic field, which had been oriented in a particular direction, began to fluctuate wildly. The count of certain particles increased, while others decreased. The data patterns that had been stable for decades suddenly became chaotic. Voyager 1 had reached the termination shock. To understand what this means, we need to understand the structure of the region dominated by our Sunday. And to understand that, we need to understand what our star actually does. Our star does not simply sit in space, passively glowing. It exhales. Constantly. Every second, the Sun releases roughly 1,000,000 tons of matter in the form of charged particles, mostly hydrogen and helium ions, along with electrons. This stream of particles, the solar wind, rushes outward in all directions at speeds ranging from 250 miles per second to 500 miles per second, depending on conditions on the Sunday. The solar wind carries with it the Sun's magnetic field, stretching it outward like taffy being pulled. This creates a vast bubble of solar influence, a region where the Sun's particles and magnetic field dominate over the material and fields of interstellar space. This bubble is called the heliosphere, and it extends billions of miles in all directions. But the solar wind cannot expand forever. Eventually, far from the Sun, it runs into the material that fills the space between stars. The interstellar medium is thin, just a few atoms per cubic centimeter, but it is not nothing, and it exerts pressure. The termination shock is the boundary where the solar wind, still traveling faster than the speed of sound in that medium, suddenly slows to subsonic speeds. It is like a sonic boom in reverse, a standing shock wave where the solar wind transitions from supersonic to subsonic flow. The particles pile up, compress, and heat as they decelerate. Beyond the termination shock lies the heliosheath, a region where the solar wind is compressed, heated, and turbulent as it pushes against the interstellar medium. The physics of the termination shock had been studied theoretically for decades. Scientists understood the basic principles. Supersonic flow, encountering an obstacle, must decelerate, and this deceleration occurs through a shock wave. But the details of what actually happens at the termination shock could only be learned by sending a spacecraft there. Voyager revealed that the termination shock is not a simple, smooth boundary. It is dynamic, moving inward and outward as the solar wind strengthens and weakens. During periods of high solar activity, when the Sun is emitting more particles, the termination shock is pushed outward. During quiet periods, it contracts. The boundary is not a wall but a membrane, flexing and responding to conditions on both sides. And beyond the heliosheath lies the heliopause, the outer boundary of the Sun's influence, the place where the solar wind stops entirely, the edge of our solar system's protective bubble, the frontier that Voyager was now approaching. In December of 2004, Voyager 1 crossed the termination shock and entered the heliosheath. It was the first human-made object to reach this region of space. Scientists had been waiting decades for this moment, eager to learn what conditions were like at the edge of the Sun's influence. What Voyager found there was strange. The heliosheath was nothing like scientists had predicted. For 27 years, Voyager had been traveling through the solar wind, that steady stream of particles flowing outward from the Sunday. The data had been consistent, predictable, almost boring in its regularity. Scientists knew what to expect because the physics was well understood. Solar wind in, solar wind measurements out. The same patterns, year after year. Now, suddenly, everything was different. The magnetic field, which had been pointing in one general direction for decades, was fluctuating wildly. Energetic particle counts were spiking and dropping in ways that made no sense. The temperature readings suggested the environment was far hotter than anyone had predicted. It was as if Voyager had left the familiar waters of a calm lake and entered the churning rapids of a river. The scientists responsible for analysing this data were both thrilled and bewildered. They had built their careers on understanding the heliosphere, and now the heliosphere was doing things they could not explain. Papers were written, conferences were held, arguments ensued. But everyone agreed on one thing. Voyager was entering territory that no human-made object had ever explored, and the real surprises were still ahead. To understand how strange the heliosheath truly was, we need to step back and consider what scientists expected to find. For decades, theoretical models had predicted a relatively simple structure. The solar wind would flow outward from the sun, hit the termination shock, slow down from supersonic to subsonic speeds, and then flow along the boundary of the heliosphere toward a tail streaming behind the sun as it moves through the galaxy. Think of it like water flowing from a hose. When the water hits a surface, it spreads out and flows along that surface. The heliosheath would be similar, a transition zone where solar material gradually redirected itself to flow along the outer boundary. The models predicted this region would be turbulent, but understandable, where solar material gradually mixed with interstellar material before reaching the final boundary. There would be eddies and fluctuations, but the overall pattern would be clear. Material in, material out, flowing around the heliosphere like air flowing around an airplane wing. What Voyager 1 found was chaos. The magnetic field in the heliosheath did not point in a consistent direction. These reversals created a foamy, bubble-like structure, with magnetic field lines wrapping around themselves in complex configurations that no model had predicted. It was as if the entire region was filled with magnetic soap bubbles, each with its own internal field direction, constantly forming and popping and reforming. The particles in the heliosheath were equally chaotic. Energetic particles that should have been flowing in one direction were instead scattered in all directions. The boundary between solar particles and cosmic rays, which scientists had expected to be relatively sharp, was instead blurred and indistinct. Some cosmic rays were getting in, some solar particles were getting out. The neat separation between inside and outside simply did not exist. Most puzzling of all was the temperature. The heliosheath was hot, not just warm, but searingly hot by the standards of space. Temperatures in the tens of thousands of degrees Kelvin. This heat was not coming from the sun, which was by now nearly 100 astronomical units away. Its light and heat diminished to a faint glow. The heat was being generated locally by processes that scientists are still working to understand. One leading theory involves magnetic reconnection. When magnetic field lines of opposite polarity are pushed together, they can snap and reconnect in new configurations. This process releases enormous amounts of energy, converting magnetic energy into heat and kinetic energy. It is the same process that powers solar flares on the surface of the Sunday. In the heliosheath, the turbulent, foamy magnetic structure may be driving constant reconnection events, heating the plasma to extreme temperatures. Another possibility involves the compression of the solar wind as it piles up against the interstellar medium. Just as air heats up when you compress it in a bicycle pump, the solar wind may be heating as it is squeezed between the onrushing interstellar material and the continuing outflow from the Sunday. The particles have nowhere to go, so they pile up and get hotter. A third possibility involves something called pickup ions. As neutral atoms from the interstellar medium drift into the heliosphere, they can be ionized by solar radiation. Once ionized, they are grabbed by the solar magnetic field and accelerated to high speeds. These pickup ions can carry enormous amounts of energy, and when they pile up in the heliosheath, they may contribute significantly to the heating. Whatever the cause, the heliosheath was far more dynamic and energetic than anyone had anticipated. The simple models of gentle flow and gradual transition had to be thrown out. The heliosheath was a churning, chaotic region where magnetic fields tangled and untangled, where particles bounced in random directions, where temperatures soared despite the enormous distance from the Sunday, scientists began referring to the heliosheath as the cosmic foam zone. It was an apt description. The magnetic field bubbles, each perhaps hundreds of millions of miles across, formed and reformed continuously, creating a structure that was neither ordered nor completely random. It was chaos with patterns, randomness with structure. The implications for our understanding of plasma physics were profound. The heliosheath was essentially a natural laboratory, demonstrating phenomena that could never be replicated on Earth. The scales were too vast, the energies too extreme, the conditions too exotic. But Voyager was there, measuring everything, sending back data that would keep plasma physicists busy for generations. And Voyager 1 was about to discover that the strangeness was only beginning. In 2012, after 8 years of travelling through the heliosheath, Voyager 1 discovered something stranger still. The spacecraft detected what scientists would later call the magnetic highway. In this region, the magnetic field lines organized themselves in an unexpected pattern. Instead of pointing in random directions as they had throughout most of the heliosheath, the field lines aligned themselves into parallel structures running perpendicular to the boundary. These aligned field lines created conduits, channels through which particles could flow freely between the heliosphere and interstellar space. Imagine a highway with multiple lanes, each lane carrying traffic in a specific direction. The magnetic highway worked similarly. Particles from outside the heliosphere could flow inward along some field lines. Particles from inside could flow outward along others. The boundary that was supposed to separate inside from outside had become porous. This was completely unexpected. The boundary was supposed to separate inside from outside. Solar particles should stay in. Interstellar particles should stay out. Instead, Voyager found cosmic highways connecting our solar system to the galaxy beyond. Particles from outside could flow in. Particles from inside could flow out. The protective bubble surrounding our solar system was riddled with holes. The magnetic highway raised as many questions as it answered. How did these aligned field structures form? The heliosheath should be chaotic, with fields pointing every which way. Why would they suddenly organize themselves into neat parallel lanes? Were these structures permanent features, or were they transient phenomena that Voyager happened to catch at just the right moment? Did they exist only in this particular region of the heliosphere, or were they a general feature of the entire boundary? Some scientists propose that the magnetic highway was a natural consequence of the heliopore's geometry. As the heliosphere pushes against the interstellar medium, the magnetic field lines get stretched and compressed. Near the boundary, where the pressure from both sides is most intense, the field lines might naturally align into the observed pattern, like logs floating in a river that align with the current. Others suggested that the magnetic highway might be related to magnetic reconnection events at the boundary. When solar and interstellar field lines of opposite polarity come together, they can reconnect, creating new field configurations. These reconnected field lines might naturally arrange themselves into the aligned structures Voyager observed. The discovery of the magnetic highway changed how scientists thought about the heliosphere. It was not a sealed bubble with impermeable walls. It was more like a tent with gaps in the seams, allowing material to flow in and out. The solar system was connected to the galaxy in ways that the simple models had not anticipated, and most importantly, what would Voyager find on the other side? Scientists had established 3 criteria for determining when Voyager had truly left the heliosphere and entered interstellar space. These criteria had been developed over decades of theoretical work and were considered the definitive markers of the heliopore's crossing. First, the count of cosmic rays should increase dramatically. Cosmic rays are high-energy particles from outside the solar system, produced by supernova explosions and other violent events in the galaxy. Inside the heliosphere, these particles are partially blocked by the Sun's magnetic field. Beyond the heliosphere, that protection falls away. An increase in cosmic ray counts would indicate that Voyager had crossed into the unshielded environment of interstellar space. Second, the count of particles originating from our Sun should drop to near zero. Inside the heliosphere, Voyager is bathed in solar wind particles streaming outward from the Sunday. Beyond the heliosphere, those particles should be absent or greatly reduced. Third, the direction of the magnetic field should change significantly. The magnetic field inside the heliosphere is generated by the Sun and carried outward by the solar wind. The magnetic field in interstellar space is generated by completely different processes and should point in a different direction. A change in field orientation would be a clear signature of the boundary crossing. In August of 2012, two of these three signatures appeared almost simultaneously. The cosmic ray count spiked dramatically over just a few days. Particles that had been partially blocked by the heliosphere suddenly flooded Voyager's detectors. The cosmic ray intensity jumped by about 9% and then stabilized at the higher level. This was exactly what the models had predicted. The protective influence of the heliosphere had fallen away. Voyager was now exposed to the full flux of galactic cosmic rays. At the same time, the count of particles originating from our Sun dropped to near zero. The solar wind, that constant companion throughout Voyager's 35-year journey, essentially disappeared. The spacecraft was no longer bathed in material streaming outward from our star. It had crossed into a region dominated by particles from beyond the solar system. The data seemed unmistakable. Two of the three criteria had been met. Voyager 1 had crossed a boundary that no human-made object had ever crossed before. The spacecraft had left the solar system and entered interstellar space. But one measurement refused to cooperate with this interpretation. The magnetic field direction barely changed at all. Scientists had predicted a dramatic shift in field orientation at the heliopause, a clear signature that Voyager had crossed from the solar-dominated region into the galaxy-dominated region. Instead, the magnetic field on both sides of the boundary pointed in almost exactly the same direction. The change was so small that it was within the measurement uncertainty of Voyager's magnetometer. This was deeply puzzling. The solar magnetic field and the interstellar magnetic field are generated by completely different processes. There was no reason to expect them to point in the same direction, and yet they did. Some scientists argued that Voyager had not truly entered interstellar space. Perhaps the spacecraft remained in some previously unknown outer region of the heliosphere, a place where cosmic rays could enter but the magnetic field retained its solar character. Perhaps there was another boundary farther out, the true heliopause, that Voyager had not yet reached. Other scientists argued that the 2 out of 3 criteria were sufficient. The cosmic ray increase and solar particle decrease were clear evidence of a boundary crossing. The magnetic field alignment must have some other explanation, perhaps something about the structure of the boundary that the models had not anticipated. The debate raged in scientific journals and conference rooms. Careers and reputations were at stake. The question of whether humanity had truly sent a spacecraft beyond the solar system became surprisingly contentious. It was no longer just a scientific question. It was a question of what it meant to leave home. Some researchers argued that the traditional 3 criteria were too rigid. The universe, they pointed out, is under no obligation to conform to our expectations. Just because the models predicted a magnetic field change did not mean nature had to provide one. The particle data was clear. Voyager had crossed a major boundary. The magnetic field discrepancy was interesting, perhaps, but it did not negate the other evidence. Others were more cautious. Science, they argued, depends on precise definitions and rigorous criteria. If we start declaring spacecraft to be in interstellar space based on partial evidence, we undermine the credibility of future claims. The debate was complicated by the intense public interest in the question. Newspapers around the world had been writing about Voyager's potential crossing for years. Everyone wanted to know, had humanity finally sent something beyond the solar system? The scientists felt the pressure of public expectation, even as they tried to maintain their objectivity. This mystery would force scientists to completely rethink what exists at the edge of our solar system. And what awaited Voyager beyond the boundary was not the cold, empty void that generations of scientists had imagined. It was something far more terrifying and beautiful. The scientific community had been preparing for this moment for decades. Theoretical physicists had written countless papers predicting what Voyager would find. Computer simulations had been run, creating virtual heliospheres and virtual interstellar media, trying to anticipate every possible scenario. Graduate students had built their dissertations around the expected crossing. Everyone thought they knew what was coming. They were wrong. The interstellar medium turned out to be nothing like the theoretical models had predicted. It was not the cold, quiet void that generations of scientists had imagined. It was not the peaceful harbour at the end of the solar wind's long journey. It was not the simple, well-behaved plasma that the equations suggested. Instead, Voyager found a region of extraordinary complexity, where temperatures soared to unexpected heights, where magnetic fields aligned in inexplicable ways, where the very definition of inside and outside became blurred. The edge of the solar system was not a boundary. It was a transformation. The interstellar medium was supposed to be cold. For decades, scientists had imagined the space between stars as a frigid void, a near vacuum at temperatures approaching absolute zero. The reasoning seemed sound. The interstellar medium is extraordinarily thin, just a few atoms per cubic centimetre. Any warmth should radiate away into the emptiness. The space between stars should be cold, dark, and silent. The interstellar medium, scientists believed, consisted of sparse atoms and molecules, mostly hydrogen, drifting through space at temperatures of just a few thousand degrees Kelvin at most. Some regions might be warmer, heated by nearby stars or supernova remnants. But generally, the space between stars should be cold enough that any spacecraft crossing into it would find itself in a deep freeze, insulated only by the vacuum itself. What Voyager 1 found was a wall of fire. The plasma surrounding our solar system, just beyond the heliopause, is heated to temperatures between 30,000 and 50,000 degrees Kelvin. That is 5 to 6 times hotter than the surface of the Sunday. The visible surface of the Sun, called the photosphere, has a temperature of about 5,800 degrees Kelvin. The interstellar medium just beyond the heliosphere is far hotter. The boundary of our solar system is not a cold frontier but a burning barrier, a shell of superheated gas encasing everything we have ever known. Every planet, every asteroid, every comet, every spacecraft, every human being that has ever lived, all of it exists inside a bubble surrounded by fire. This finding shocked the scientific community. It contradicted decades of theoretical predictions. It challenged fundamental assumptions about the structure of interstellar space, and it raised immediate questions about how a spacecraft, or anything else, could possibly survive crossing such a barrier. The answer lies in the density of the plasma. Temperature, in physics, is a measure of the average kinetic energy of particles. In a hot gas, particles are moving very fast. In a cold gas, they are moving slowly. When fast-moving particles collide with something, they transfer energy. That is how heat works in everyday experience. Touch a hot stove, and the fast-moving particles in the metal transfer energy to the slower-moving particles in your skin. You feel this energy transfer as heat, but temperature says nothing about how many particles there are. The interstellar medium is extraordinarily sparse. Near the heliopause, there is roughly 1 atom per cubic centimetre. That is 1 single atom in a space the size of a sugar cube. For comparison, the air you are breathing contains about 10 to the 19th power molecules per cubic centimetre. That is a 1 followed by 19 zeros. The interstellar medium is roughly 20 quintillion times less dense than the atmosphere of Earth. What this means is that even though individual particles in the interstellar medium are moving very fast, there are so few of them that they cannot transfer significant heat to a spacecraft passing through. Voyager 1 is struck by these fast-moving particles, but so rarely that the net heating effect is negligible. It is like walking through a room where someone is occasionally throwing ping-pong balls at very high speed. Each ball carries energy, but there are so few of them that you barely notice. The spacecraft passes through the wall of fire essentially unharmed. Its temperature is determined by the balance between heating from the distant sun and cooling by radiation into space, not by the hot plasma surrounding it. The wall of fire is real, but it is a fire without fuel, a burning that does not burn. This discovery had immediate practical implications. Engineers planning future interstellar missions had worried about how spacecraft would survive the extreme temperatures at the edge of the solar system. The wall of fire sounded terrifying, but Voyager's experience demonstrated that the terror was misplaced. A spacecraft could cross the boundary with no special thermal protection at all. The discovery also had profound implications for our understanding of stellar environments throughout the galaxy. If our sun is surrounded by a wall of fire, then presumably other stars are too. Every star with a stellar wind pushing against the interstellar medium should create a similar boundary, a shell of superheated plasma marking the edge of its influence. The galaxy might be filled with these invisible fires, burning at the edges of every stellar system. But the existence of this superheated plasma raises profound questions. Where does the heat come from? What process maintains these extreme temperatures in the void between stars? The interstellar medium has no obvious heat source. There is no nearby star to warm it, no nuclear reactions to power it. And yet, it burns. Several mechanisms have been proposed. One possibility is shock heating. As the solar wind pushes outward against the interstellar medium, it creates a shock wave, a boundary where material is compressed and heated. This is similar to how a sonic boom works. When an airplane exceeds the speed of sound, air molecules pile up in front of it faster than they can move out of the way. This creates a shock wave, and the compression heats the air. The heliopause itself may be a site of continuous shock heating, with the interaction between solar and interstellar material generating temperatures far higher than either medium would have in isolation. Another possibility is magnetic reconnection. The interstellar magnetic field, like the solar magnetic field, is tangled and complex. When field lines of opposite polarity are pushed together, they can reconnect explosively, releasing energy that heats the surrounding plasma. Every time two field lines snap and reconnect, a tiny explosion of energy heats the local plasma. Millions of these events, happening constantly across billions of miles, could maintain the extreme temperatures. A third possibility involves pickup ions. As neutral atoms from the interstellar medium drift into the heliosphere, they can be ionized by solar ultraviolet radiation. Once ionized, they are grabbed by the solar magnetic field and accelerated to high speeds. These newly created ions are then carried outward by the solar wind, gaining energy as they go. When these energetic pickup ions reach the boundary region, they may deposit their energy into the local plasma, heating it to extreme temperatures. The truth likely involves all of these mechanisms, and perhaps others we have not yet identified. The boundary of our solar system is far more dynamic and energetic than anyone had imagined. It is a place of constant activity, where shock waves compress material, magnetic fields reconnect and release energy, and particles are accelerated to enormous speeds. Far from being a quiet frontier, the edge of the heliosphere is a churning cauldron of plasma physics. But the wall of fire was not the only surprise waiting beyond the heliopause. In 2017, 5 years after crossing into interstellar space, Voyager 1 detected something unexpected in its plasma wave data. The spacecraft heard a sound, not a sound in the conventional sense. Space is a vacuum. Sound waves, which require a medium to propagate, cannot travel through interstellar space the way they travel through air or water. You cannot stand in interstellar space and hear anything, because there is nothing to carry the vibrations to your ears. But Voyager's plasma wave instrument can detect oscillations in the density of charged particles, electrical signals that correspond to variations in the plasma surrounding the spacecraft. These oscillations are not sound waves, but they are analogous to sound waves. They represent compressions and rarefactions in the plasma, regions of higher and lower density that propagate through space. What Voyager detected was a persistent, low-frequency hum, a cosmic drone at a frequency of about 3 kHz. If you could somehow hear it, it would sound like a deep, steady tone, unchanging and eternal. This hum continued without interruption, day after day, month after month, year after year. It represented oscillations in the interstellar plasma, vibrations in the medium between stars. Scientists call this the plasma wave emission. Its frequency allows them to calculate the density of the interstellar medium with remarkable precision. The frequency of plasma oscillations depends on how many charged particles are present. By measuring the frequency, scientists can determine the density. The persistent hum became a tool for studying the environment Voyager was passing through, and its persistence reveals something profound about the space between stars. Far from being empty and silent, interstellar space is filled with a faint but constant cosmic hum, a background noise generated by processes that pervade the galaxy. The universe is humming to itself, and Voyager was the first human-made object to hear it. Some scientists have compared it to a persistent rain, gentle, continuous, unending. Others have called it the voice of the galaxy itself, the sound of the Milky Way breathing. It is a reminder that even in the vast emptiness between stars, things are happening, processes are unfolding, energy is flowing. The cosmic hum is not constant in frequency. It shifts slightly as the density of the interstellar medium varies along Voyager's path. When the spacecraft passes through denser regions, the frequency increases. When it passes through sparser regions, the frequency decreases. These variations create a kind of cosmic music, a symphony played on an instrument billions of miles long. Scientists have used these frequency variations to map the density of the interstellar medium along Voyager's trajectory. The results have been surprising. The density is not uniform. There are clumps and voids, regions of higher and lower concentration that reflect the turbulent history of our galactic neighborhood. Supernova explosions, stellar winds, the collapse of gas clouds to form new stars, all of these processes have left their mark on the interstellar medium. The discovery of the cosmic hum added another piece to the puzzle of interstellar space. But the biggest mystery of all remained the magnetic field. Scientists had expected that crossing the heliopause would produce a dramatic change in the magnetic field direction. This expectation was fundamental to their models of heliospheric structure. It was one of the 3 criteria for confirming that Voyager had truly entered interstellar space. The magnetic field inside the heliosphere is generated by our Sun and carried outward by the solar wind. It spirals in what is called the Parker spiral pattern, named after physicist Eugene Parker, who first predicted it in 1958. As the Sun rotates, it drags the magnetic field lines with it, creating a spiral pattern like water spraying from a rotating sprinkler. The direction this field points depends on where in the Sun's rotation cycle you measure it and how far from the Sun you are. But fundamentally, the heliospheric magnetic field is solar in origin. The magnetic field outside the heliosphere should be completely different. The interstellar magnetic field is generated by currents flowing through the Milky Way galaxy over vast distances. It is shaped by the rotation of the galaxy, by supernova explosions that create expanding bubbles of hot gas, by the dynamics of star formation in giant molecular clouds. The interstellar field has nothing to do with our Sunday. It would exist even if our star had never formed. It is a relic of processes that have been unfolding for billions of years across thousands of light years. Because these 2 fields have independent origins, scientists expected them to point in completely different directions. The odds that they would happen to align seemed vanishingly small. When Voyager crossed from the heliosphere into interstellar space, the magnetometer should have recorded a sudden change in field direction. This directional shift was considered one of the most definitive signatures of the heliopause crossing. It did not happen. The magnetic field on both sides of the heliopause pointed in almost exactly the same direction. The change was so small that some scientists argued Voyager had not truly entered interstellar space at all. Perhaps the spacecraft remained in some previously unknown outer region of the heliosphere, a place where cosmic rays could enter, but the magnetic field retained its solar character. The debate raged for over a year. Scientific conferences became battlegrounds, where researchers defended competing interpretations of the same data. Papers were published, claiming Voyager had entered interstellar space. Other papers argued it remained within the Sun's domain. Reputations were at stake. The question of whether humanity had truly sent a spacecraft beyond the solar system hung in the balance. Finally, in September of 2013, NASA officially announced that Voyager 1 had crossed the heliopause and entered interstellar space. The crossing occurred on August 25, 2012, at a distance of approximately 121 astronomical units from the Sunday. That is 121 times the distance from Earth to the Sun. About 11 billion miles. Humanity had sent an object beyond the protective bubble of our star. The announcement was covered by news media around the world. It was a historic moment, one of those rare achievements that captures the imagination of people everywhere. For the first time, something made by human hands was traveling through interstellar space, the vast realm between the stars that our ancestors could only gaze at and wonder about. The Voyager team gathered at the Jet Propulsion Laboratory in Pasadena, California, to celebrate. Many of them had worked on the mission for decades. Through budget cuts and equipment failures and the slow degradation of the spacecraft's power supply, they had kept Voyager alive through sheer determination, and now their efforts had been rewarded with a discovery that would be remembered for centuries. The resolution came as scientists developed new models that could explain the puzzling magnetic field alignment. The key insight was that the heliopause is not a passive boundary. It does not simply separate solar from interstellar domains without affecting either. The boundary actively shapes both regions through billions of years of interaction. As the solar wind pushes outward against the interstellar medium, it drags magnetic field lines with it. The interstellar field does not simply stop at the heliopause, it is pushed back, compressed, redirected. Over 4.5 billion years, this constant pressure has gradually aligned the interstellar magnetic field near the heliopause with the solar magnetic field inside it. The two fields have achieved a kind of equilibrium, each influencing the other until they point in approximately the same direction. This means the interstellar medium near our solar system is not pristine. It is not the raw, unaltered material of the galaxy. Our Sun has modified its galactic neighborhood, reshaping magnetic field directions across distances of billions of miles. The conditions Voyager measured in interstellar space may not be representative of conditions elsewhere in the galaxy. We have imprinted ourselves on the cosmos. 6 years later, in November of 2018, Voyager 2 followed its twin across the boundary. The second spacecraft had travelled a different path, crossing at a different angle to the heliosphere. Scientists eagerly compared measurements from the two crossings, hoping to learn more about the structure of the boundary. Voyager 2's crossing was in many ways more valuable scientifically than Voyager 1's. The second spacecraft still had a working plasma science instrument, which had failed on Voyager 1 in 1980. This instrument could directly measure the properties of the plasma, providing data that Voyager 1 could only infer indirectly. The crossing gave scientists their first direct measurements of interstellar plasma. The data confirmed many of the findings from Voyager 1 while adding new details. The interstellar plasma was indeed hot, tens of thousands of degrees, just as Voyager 1 had suggested. The cosmic ray flux was similar at both crossing points. The magnetic field showed the same puzzling alignment. Whatever was happening at the boundary, it was not a local phenomenon. It was a fundamental feature of the heliosphere's interaction with interstellar space. The wall of fire appeared at both locations. Both spacecraft detected plasma at tens of thousands of degrees Kelvin surrounding the heliosphere. The magnetic field alignment was similar at both sites, confirming that this was a large-scale phenomenon rather than a local quirk. The cosmic hum was detected by both spacecraft, demonstrating that plasma oscillations pervade the interstellar medium in our galactic neighborhood, but the exact boundary location differed between the two spacecraft. Voyager 2 crossed the heliopause at approximately 119 astronomical units from the Sun, roughly 2 astronomical units closer than Voyager 1's crossing at 121 astronomical units. While this difference of nearly 200 million miles might seem small compared to the total journey of more than 11 billion miles, it revealed important information about the heliosphere's shape. The 2 astronomical unit difference translates to about 186 million miles, roughly twice the distance from Earth to the Sunday. It is a significant variation, indicating that the heliosphere is not a uniform sphere but a complex asymmetric structure shaped by both solar activity and the properties of the surrounding interstellar medium. Our solar system is not surrounded by a perfect sphere but by an elongated bubble, pushed back by our Sun's motion through the interstellar medium. The Sun is moving through the galaxy at about 450,000 miles per hour, and this motion compresses the heliosphere on the leading edge and stretches it out behind. The heliosphere has a nose pointed in the direction of our Sun's galactic motion and a tail streaming behind like the tail of a comet. Some scientists have proposed that the heliosphere might have 2 tails, like a pair of comet tails, shaped by the interaction between the solar wind and the interstellar magnetic field. Others have suggested that the tail might be much shorter than previously thought, truncated by instabilities in the boundary. The exact shape remains a subject of active research. Voyager 1 crossed closer to the nose of the heliosphere, where the boundary is pushed in by the ram pressure of interstellar material. Voyager 2 crossed at a different angle, sampling a slightly different part of the boundary structure. The 2 astronomical unit difference in crossing distances reflects this asymmetry. Future spacecraft crossing at other angles would likely find the boundary at still different distances, mapping the 3-dimensional shape of our Sun's protective bubble. The comparison between the 2 crossings revealed other differences as well. Voyager 2 detected a sharper boundary than Voyager 1 had. The transition from heliospheric to interstellar conditions occurred over a shorter distance, suggesting that the boundary structure varies from place to place. The heliopause is not a uniform membrane but a complex textured surface with different properties at different locations. Scientists also noticed that the density of interstellar plasma differed slightly between the 2 crossing points. This variation hints at structure in the interstellar medium itself, clumps and voids in the gas that fills the space between stars. The data from both Voyagers is helping to map this structure, revealing the texture of interstellar space on scales of billions of miles. Together, the 2 Voyager spacecraft have transformed our understanding of the boundary between our solar system and interstellar space. They have revealed a region far more complex, dynamic, and mysterious than anyone had imagined. A wall of fire surrounding our cosmic home, a persistent hum echoing through the void, magnetic fields aligned by billions of years of interaction between our Sun and the galaxy beyond. But what does all this mean for the universe beyond? What are the implications of these discoveries for life, for exploration, for humanity's place in the cosmos? These questions haunted the scientists who analyzed Voyager's data. They had set out to understand the boundary of our solar system, and instead they had discovered a cosmic phenomenon that raised more questions than it answered. The wall of fire, the cosmic hum, the aligned magnetic fields, all of these findings pointed to a universe far more complex and interconnected than anyone had imagined. The data continued to stream back from Voyager, 22 hours after it was collected, traveling at the speed of light across billions of miles of empty space. Each day brought new measurements, new puzzles, new opportunities to revise our understanding of the cosmos. The spacecraft that had been designed for a 4-year mission was still doing science nearly 50 years after launch, still surprising us, still teaching us about the universe we inhabit, and the implications of what it had found stretched far beyond our solar system. To every star in the galaxy, and perhaps to every star in the universe, the discoveries at the edge of our solar system reach far beyond our local cosmic neighborhood. They have implications that stretch across the galaxy and touch the fundamental questions of life, habitability, and humanity's place in the universe. Consider first what the heliosphere does for us. The space between stars is filled with cosmic rays, high-energy particles traveling at nearly the speed of light. These are not the gentle photons of starlight. These are protons, electrons, and heavier nuclei that have been accelerated to enormous energies by the most violent events in the universe. Supernova explosions, the death throes of massive stars, send shockwaves racing through the galaxy that accelerate particles to incredible speeds. Active galactic nuclei, the supermassive black holes at the centers of galaxies, launch jets of material that can energize particles even further. The shockwaves from colliding galaxies, events that unfold over hundreds of millions of years, contribute their share of cosmic ray acceleration. These particles carry enough energy to damage DNA, disrupt electronics, and pose serious health risks to any unprotected organism. A single cosmic ray can punch through a cell nucleus, breaking the delicate strands of genetic material. Most of the time, the cell can repair the damage, but occasionally the repair is imperfect and mutations result. Some of these mutations are harmless. Some cause cancer. Some, over evolutionary timescales, drive the changes that shape the development of life. Cosmic rays also pose a threat to electronics. When a high-energy particle strikes a microchip, it can flip bits, corrupting data or causing software crashes. This is a well-known problem for satellites and spacecraft, which must be designed with error-correcting systems to handle cosmic ray impacts. Voyager itself has experienced cosmic ray hits that temporarily disrupted its systems, though the spacecraft has always recovered. On Earth, we are protected from most cosmic rays by a combination of the heliosphere, our planet's magnetic field, and our thick atmosphere. By the time cosmic rays reach the surface, most of their energy has been absorbed. But in space, or on planets without strong magnetic fields and thick atmospheres, cosmic ray exposure is much higher. The heliosphere acts as a shield. The Sun's magnetic field, carried outward by the solar wind, deflects many of these dangerous particles before they can reach the inner solar system. The particles encounter the magnetic field and are bent away, following curved paths that carry them around the heliosphere rather than through it. Voyager's measurements show that cosmic ray intensity increases by roughly 9% immediately beyond the heliopause. Over the full depth of the heliosphere, from heliopause to Earth, the protection is even greater. Life on Earth exists in part because our Sun creates this protective bubble. Without the heliosphere, cosmic ray bombardment at Earth's surface would be significantly higher. The atmosphere provides additional protection, absorbing many cosmic rays before they reach the ground. But for life in space, or for life on planets with thinner atmospheres, the heliosphere's protection could be the difference between survival and extinction. The biological effects of cosmic ray exposure are well documented from studies of astronauts and high-altitude pilots. Cosmic rays can damage DNA, causing mutations that may lead to cancer or other diseases. They can also damage the central nervous system, potentially causing cognitive decline over long exposures. Any future human missions beyond the heliosphere will need to address these risks. For life that evolved within the heliosphere, cosmic ray shielding is simply part of the environment. We take it for granted, like the oxygen in our atmosphere or the magnetic field that protects us from solar wind particles. But step outside the heliosphere, and that protection vanishes. The radiation environment becomes harsher, more dangerous, less forgiving, but the heliosphere is not static. As our solar system orbits the galactic center, completing one revolution every 225 million years. It passes through regions of varying density in the interstellar medium. When we encounter denser regions, where there are more interstellar particles per cubic centimeter, the heliosphere is compressed. The pressure from outside pushes the boundary inward, shrinking our protective bubble. When we pass through more diffuse regions, the heliosphere expands, the reduced external pressure allowing the solar wind to push farther out. The level of cosmic ray protection Earth receives varies over geological timescales. There have been times in Earth's history when the heliosphere was larger than it is today, and times when it was smaller. These variations could have biological consequences. Some scientists have proposed that mass extinctions in Earth's history may correlate with periods when the heliosphere was compressed by dense interstellar clouds. A smaller heliosphere would provide less cosmic ray shielding, allowing more high-energy particles to reach the inner solar system. This increased radiation could cause increased mutation rates in organisms, disrupting ecosystems and potentially triggering extinction cascades. It could also affect climate, as cosmic rays influence cloud formation in the atmosphere. The evidence for this hypothesis remains controversial. Correlating events that happened hundreds of millions of years ago with the Sun's position in its galactic orbit is extremely difficult. The geological record is incomplete, and the uncertainties in reconstructing the Sun's past trajectory through the galaxy are enormous. But the hypothesis highlights how deeply connected our planet is to the cosmic environment. We are not isolated in our little solar system. We are embedded in a galaxy, and the galaxy shapes our destiny. Some researchers have attempted to identify specific interstellar clouds that the solar system may have passed through in the past. Analysis of deep-sea sediments has revealed layers enriched in iron 60, a radioactive isotope produced in supernova explosions. These layers, dating to about 2 to 3 million years ago, suggest that the solar system passed relatively close to a supernova remnant, a region of space enriched with the debris of an exploding star. The heliosphere may have been compressed during this passage, allowing more cosmic rays and supernova debris to reach Earth. The discoveries at the heliopause also have implications for the search for life elsewhere in the galaxy. Every star with a stellar wind will create some kind of astrosphere. The size and structure of these astrospheres will vary depending on the star's mass, age, activity level, and the local density of interstellar material. Young, active stars tend to have stronger stellar winds and larger astrospheres than older, quieter stars. Our Sun was more active in its youth, and its heliosphere was probably larger 4 billion years ago than it is today. As stars age, they gradually spin down, their magnetic activity decreases, and their stellar winds weaken. The astrospheres of old stars may be barely larger than their planetary systems. The local interstellar medium also matters. Our Sun is currently passing through a region called the local interstellar cloud, a relatively warm and diffuse patch of space. In this environment, the heliosphere can extend to roughly 120 astronomical units. But when the Sun passes through denser regions of the interstellar medium, as it will in the future, the heliosphere may be compressed to half that size or less. Massive hot stars have powerful stellar winds that can create enormous astrospheres, extending tens or even hundreds of astronomical units in all directions. These stars burn bright and hot, pumping out vast quantities of particles that push the interstellar medium back. But massive stars are also short-lived, burning through their fuel in just a few million years before exploding as supernovae. There may not be time for life to evolve within their protective bubbles. Smaller, cooler stars like red dwarfs have weaker stellar winds and may create much smaller astrospheres. Some may have astrospheres that barely extend beyond their planetary systems. Planets orbiting these stars would receive less protection from cosmic rays, potentially exposing any life there to higher radiation levels. On the other hand, red dwarfs live for trillions of years, giving life far more time to evolve and adapt. For a planet to be habitable, it may need to exist within a sufficiently protective astrosphere. Too small an astrosphere, and the planet would be bombarded by cosmic rays with all the biological consequences that implies. Too unstable an astrosphere, perhaps around a star with highly variable activity, and the radiation environment would fluctuate wildly, making it difficult for life to establish a foothold. The Goldilocks zone for habitability may need to include not just the right distance from a star for liquid water, but also the right position within a protective stellar bubble. A planet at the perfect distance for liquid water might still be inhospitable if it lies beyond its star's astrosphere, exposed to the full flux of galactic cosmic rays. This insight could transform how we think about the Drake equation, the famous formula for estimating the number of intelligent civilizations in the galaxy. The equation includes terms for the fraction of stars with planets, the fraction of planets that are habitable, and so on. Voyager's discoveries suggest that we may need to add another term, the fraction of habitable planets that are also protected by adequate astrospheres. For planets orbiting red dwarf stars, the most common type of star in the galaxy, this consideration could be particularly important. Red dwarfs are smaller and cooler than the Sun, and their stellar winds are generally weaker. Their astrospheres may be correspondingly smaller, offering less protection from cosmic rays. On the other hand, habitable planets around red dwarfs must orbit very close to their stars to receive enough warmth for liquid water. This close proximity might place them well within even a modest astrosphere. The interplay between stellar luminosity, stellar wind strength, and orbital distance creates a complex web of factors that influence habitability. This means that when we search for habitable exoplanets, we may need to consider not just the planet itself, but the space environment created by its star. A planet in the traditional habitable zone might still be inhospitable if its star fails to create adequate cosmic ray shielding. Conversely, a planet slightly outside the traditional zone might be more habitable than expected if its star provides exceptional protection from the galactic radiation environment. Voyager's discoveries also have practical implications for future space exploration. Any spacecraft traveling to another star will need to cross through the wall of fire at the edge of our solar system, and then traverse the interstellar medium for years or decades or centuries before reaching its destination. The conditions Voyager has measured, the extreme temperatures, the cosmic ray flux, the plasma oscillations, these will define the environment that interstellar spacecraft must be designed to withstand. The good news is that Voyager has demonstrated this passage is possible. Despite being built with 1970s technology, with computers less powerful than a modern calculator, the spacecraft has survived the crossing essentially intact. Its instruments continue to function, its power systems continue to operate, its communication systems, though weakened by distance, still send data back to Earth. The wall of fire, while dramatic, is not a barrier to spacecraft with even modest engineering. The sparse density of the interstellar plasma means that actual heat transfer to a spacecraft is minimal. Cosmic rays are a concern, but proper shielding can mitigate their effects. The challenges of interstellar space are real, but they are not insurmountable. The challenges of interstellar travel remain immense, but they are challenges of scale rather than fundamental physics. The distances are vast, requiring travel times measured in tens of thousands of years with current technology. The nearest star system, Alpha Centauri, is about 4 light-years away. At Voyager's speed of 38,000 miles per hour, reaching Alpha Centauri would take about 70,000 years. That is longer than modern humans have existed. To put this in perspective, 70,000 years ago, our ancestors were still sharing the planet with Neanderthals. Agriculture had not been invented. Writing did not exist. The great civilizations of Egypt, Greece, and Rome were unimaginably far in the future. If we had launched a spacecraft at Voyager's speed 70,000 years ago, it would only now be arriving at Alpha Centauri. The energy requirements are enormous, requiring propulsion systems far beyond anything we have yet built. Chemical rockets, even nuclear rockets, cannot achieve the speeds needed for practical interstellar travel. More exotic propulsion concepts, like solar sails, laser propulsion, or antimatter engines, might someday make interstellar journeys feasible in human lifetimes, but these technologies remain in the early stages of development. Solar sails, for instance, could use the pressure of sunlight to gradually accelerate a spacecraft to high speeds. By making the sail thin and light, you can achieve accelerations that, over time, add up to impressive velocities. A solar sail that unfurled close to the sun, where sunlight is most intense, could potentially reach speeds of several 100,000 miles per hour, much faster than Voyager. Laser propulsion takes this concept further. Instead of relying on sunlight, a powerful laser array in the inner solar system could beam concentrated light at a sail-equipped spacecraft, accelerating it to a significant fraction of light speed. The Breakthrough Starshot initiative has proposed using this technique to send tiny probes to Alpha Centauri, potentially arriving in just 20 years instead of 70,000. But there are no barriers, no walls we cannot pass through. The wall of fire is hot but harmless. The cosmic ray flux is manageable with proper shielding. The vast distances are daunting but not infinite. Someday, if we choose to make the effort, we will send spacecraft to other stars. We will cross the heliosphere and the interstellar void and arrive at new worlds around alien suns. Voyager 1 has proven that. As I speak these words, Voyager 1 continues its journey outward. It is now more than 165 astronomical units from the Sun, more than 15 billion miles from home. Every hour, it travels another 38,000 miles farther. Every day, it adds almost 1 million miles to its distance. Every year, it moves about 3.5 astronomical units farther from the Sun that gave it birth. Despite nearly 50 years of travel, the spacecraft has barely begun its journey through the structures surrounding our solar system. The heliosphere, that protective bubble Voyager spent 35 years reaching and crossing, represents only the innermost boundary. Far greater distances lie ahead. The Oort cloud awaits. That vast spherical shell of icy bodies marks the outer boundary of our Sun's gravitational influence, the region where the Sun's gravity is still strong enough to hold objects in orbit. The Oort cloud is thought to contain billions or even trillions of comets, remnants of the solar system's formation that were ejected to the outer reaches by gravitational interactions with the giant planets. These comets are the detritus of creation, the leftover building blocks that did not become planets. They are pristine samples of the material from which the solar system was formed, preserved in the cosmic deep freeze of the outer solar system. Every comet that streaks across our sky, trailing a glowing tail of vaporized ice, began its journey in the Oort cloud, disturbed from its ancient orbit by the gravitational tug of a passing star or the distant influence of the galactic tide. The inner edge of the Oort cloud lies at roughly 2,000 astronomical units from the Sunday. The outer edge may extend to 100,000 astronomical units, nearly a third of the way to Alpha Centauri. At Voyager's current speed of roughly 3.5 astronomical units per year, reaching the inner edge will require another 500 years. Crossing through the cloud to reach true interstellar space, the region where the Sun's gravity no longer dominates, will take 30,000 years more. 30,000 years. That is longer than the history of human civilization. 30,000 years ago, humans were painting on cave walls in France and Spain, creating the first art. If those ancient artists had launched a spacecraft at Voyager's speed, it would only now be emerging from the Oort cloud and entering true interstellar space. The spacecraft that has already travelled farther than any human-made object in history has barely begun its journey through the structures surrounding our solar system. The heliosphere, though vast, is merely the innermost layer of a cosmic onion. The Oort cloud extends perhaps 1,000 times farther still. Voyager will not survive to complete this journey. Its plutonium power source is decaying, losing about 4 watts of electrical power each year to the immutable laws of physics. When Voyager launched in 1977, its radioisotope thermoelectric generators produced about 470 watts. Today, they produce less than half that amount. Engineers have already shut down heaters, turned off instruments, and implemented every power-saving measure they can devise. The power decline follows an exponential curve, the same curve that governs all radioactive decay. The plutonium-238 that powers Voyager has a half-life of about 87 years. Every 87 years, half of the remaining plutonium decays into uranium, releasing slightly less heat to be converted into electricity. There is no way to stop this process. No way to slow it down. No way to replenish the fuel from across 15 billion miles of space. The engineers have become masters of power conservation. They have learned which instruments can be turned off and for how long. They have developed clever schemes to share power between subsystems, turning off one instrument to power another, then switching back. They have adjusted operating procedures to minimize power consumption during critical measurements. Every watt saved extends the mission by a little longer. But physics is relentless. By approximately 2030, Voyager 1 will no longer have enough power to operate any of its science instruments. The last measurements will be taken, the last data transmitted. By 2036, it will likely go silent forever, its radio transmitter finally succumbing to the power shortage that has been slowly strangling it for decades. But the spacecraft will continue. Long after its last transmission, long after its instruments have frozen in the interstellar cold, Voyager 1 will still be travelling. It will coast on its current trajectory, slowing slightly as the sun's gravity tugs at it from behind but never stopping. It will pass through the Oort cloud like a bullet through fog, too fast to be captured by any comet's gravity, too small to be noticed by any observer. The journey through the Oort cloud will take tens of thousands of years, but Voyager will not be alone in that vast shell of ice and rock. Trillions of comets orbit there, some as large as mountains, others no bigger than houses. They drift in the darkness, unchanged since the solar system's birth, waiting for gravitational perturbations to send them tumbling toward the inner solar system. Voyager will pass by some of these ancient wanderers, though the distances will still be enormous by human standards. The Oort cloud is vast but sparse, with typical distances between objects measured in millions of miles. The chances of Voyager actually colliding with anything are vanishingly small. It will drift through like a ghost, unseen and unseeing, carrying its golden cargo toward the stars. In about 40,000 years, it will pass within 1.6 light-years of Gliese 445, a star in the constellation Camelopardalis. It will not enter that star's planetary system. The approach is far too distant for that. Gliese 445 is an orange dwarf star, smaller and cooler than our Sunday. It currently lies about 17 light-years from Earth, but it is moving toward us. In about 40,000 years, when Voyager makes its closest approach, Gliese 445 will have moved much closer to the Sun's current position. The encounter is more a matter of the star coming to Voyager than Voyager going to the star. After the Gliese 445 encounter, Voyager will continue on through the galaxy. It will pass other stars, though none as closely for millions of years. The galaxy is simply too vast, and the stars too widely spaced, for close encounters to be common. Voyager will drift through the voids between stars, a tiny artifact of a civilization that lived on a small planet orbiting an ordinary star. It will continue drifting through the galaxy for billions of years, circling the galactic center as the Sun itself does, but on a slightly different orbit. The Sun and Voyager will grow farther and farther apart as the ages pass. Eventually, they will be on opposite sides of the galaxy from each other, separated by tens of thousands of light-years. And mounted on its side, protected by the vacuum of space from corrosion and decay, the golden record will endure. The golden record is made of gold-plated copper, chosen for its durability. Gold does not tarnish or corrode. Copper provides a stable substrate. The vacuum of space eliminates oxidation and chemical degradation. In the absence of atmosphere, weather, and biological activity, the record could last for billions of years, far longer than any artifact on Earth. The record is protected by an aluminum cover that shields it from micrometeorite impacts. Small particles of dust and ice fill interstellar space, left over from comets and asteroids and the general debris of cosmic evolution. These particles could erode an exposed surface over millions of years. The cover provides a sacrificial layer, absorbing impacts that might otherwise damage the record itself. The cover also carries the instructions for playing the record, encoded in symbolic form. These instructions assume nothing about the recipient, except intelligence and curiosity. They show how to extract the record, how to construct a stylus, how to determine the correct playback speed. They use the fundamental constants of nature, the same constants that would be measured by any technological civilization, as a basis for communication. There is something profound about this. We built a machine in 1977. We attached to it a message, a greeting, a time capsule of who we were and what we dreamed. We launched it into the cosmos with no expectation that it would ever be found, no certainty that anyone would ever hear our voice. The odds of another civilization encountering Voyager are vanishingly small. The galaxy is vast, and Voyager is tiny, and the chances of intersection are remote almost beyond calculation, and yet we sent it anyway. This is perhaps what makes Voyager's journey so moving. It is not just a scientific mission, though it has produced extraordinary science. It is not just an engineering achievement, though it represents some of humanity's finest engineering. It is an act of hope, a message in a bottle thrown into a cosmic ocean, with faith that someday, somewhere, someone might find it. The chances are vanishingly small. The galaxy contains hundreds of billions of stars spread across a disk 100,000 light-years wide. Even if intelligent civilizations exist elsewhere, the odds that one would encounter our tiny spacecraft in the immensity of interstellar space approach zero. The galaxy is simply too big, and Voyager is simply too small. Voyager may drift forever without ever being found. It may circle the galaxy for billions of years, outlasting the sun itself, and never encounter another intelligent being. The golden record may never be played. Anne Druyan's brainwaves may never be decoded. The sounds of Earth may echo forever in silence, but we sent it anyway, because that is what humans do. We reach, we explore, we send our voice into the darkness, not knowing if anyone will answer. We push beyond every boundary, every limit, every edge we encounter. The termination shock, the heliosheath, the heliopause, the wall of fire. Each obstacle we meet, we find a way through. Voyager 1 has now travelled farther from home than any object humanity has ever created. It has crossed boundaries that no other human-made artifact has crossed. It has measured environments that no other human instrument has measured. It has discovered phenomena that no other human mission has discovered, and it continues, even now, pushing outward into the unknown. In a universe that can seem cold and indifferent, this tiny spacecraft represents something remarkable about our species. We are curious, we are brave. We are unwilling to accept that any frontier is truly final. We see boundaries, and we cross them. We see distances, and we traverse them. We see darkness, and we carry our light into it. The wall of fire at the edge of our solar system turned out to be not a barrier but a doorway. Voyager passed through it and found itself in a new realm. A place where the sun's influence finally gives way to the vast interstellar medium. A place where the hum of the galaxy replaces the roar of the solar wind. A place where humanity has never been before. And somewhere in that darkness, growing fainter with each passing year, a golden record carries the sounds of Earth. Waves on a beach, thunder over a plain, the cry of a baby, the music of Beethoven, greetings in 55 languages, and the brainwaves of a woman in love. This is what Voyager found at the edge of the solar system. Not just particles and fields and temperatures, not just scientific data and engineering telemetry, but evidence that boundaries are made to be crossed, that the unknown is waiting to be known, that even a wall of fire cannot stop a species determined to explore. Voyager's journey is far from over. In one sense, it has barely begun. The spacecraft will continue traveling for billions of years, longer than the sun will shine, longer than the Earth will remain habitable, longer perhaps than human beings will exist in any recognizable form. It is our emissary to eternity, our ambassador to the ages. And in a sense, our journey is far from over too. We have sent 2 spacecraft beyond the heliosphere. Just 2 in all of human history. But we have proven it can be done. We have shown that the wall of fire can be crossed, that the interstellar medium can be navigated, that the vast distances between stars are challenging but not impossible. Someday, we will send more. Someday, we will send spacecraft that are faster and smarter and more capable than Voyager. Someday, we will send probes that can reach other star systems in decades instead of millennia. Someday, perhaps, we will send ourselves. NASA and other space agencies are already planning the next generation of interstellar probes. The Interstellar Probe mission concept, currently under study, would launch in the 2030s and travel 3 times faster than Voyager, reaching the heliopause in just 15 years instead of 35. It would carry modern instruments capable of measurements that Voyager's 1970s technology cannot make. It would map the 3-dimensional structure of the heliosphere in unprecedented detail. Other concepts are even more ambitious. The Breakthrough Starshot initiative aims to send tiny probes to Alpha Centauri at 20% of the speed of light, reaching the nearest star system in just 20 years. These probes would be pushed by powerful lasers, accelerating at thousands of times the force of gravity, reaching speeds that Voyager can only dream of. The technology is still in development, but the physics is sound. Voyager has shown us the way. It has crossed the boundaries that we were afraid to cross. It has measured the environments that we did not understand. It has survived the obstacles that we thought might be insurmountable. And it has sent back data that is rewriting our understanding of the cosmos. The stars are waiting. They have always been waiting. Since the first human looked up at the night sky and wondered what those points of light might be, they have been waiting. Since the first astronomer realized that the stars were other suns, impossibly distant, they have been waiting. Since the first rocket scientist dreamed of traveling to other worlds, they have been waiting. And now, for the first time in human history, something made by human hands is actually among them. Voyager 1 is no longer in our solar system. It is in interstellar space, the space between the stars, the realm that humans have dreamed about for millennia. It is a small spacecraft, built with primitive technology by the standards of what we might someday achieve. It carries a tiny payload of instruments, powered by a decaying nuclear battery that will fall silent within the decade. It has no means of propulsion, no way to change course, no hope of ever being recovered. But it is there. It is actually there, in interstellar space, where no human artifact has ever been before. And mounted on its side, it carries a message from a species that refuses to be confined to one small planet, orbiting one ordinary star in one ordinary galaxy. We are the people who sent a recording of a woman falling in love to the stars. We are the people who attached a cosmic map to a spacecraft and hoped someone might follow it home. We are the people who heard about a wall of fire at the edge of the solar system and flew straight through it. That is what Voyager found at the edge of the solar system. Not just the wall of fire, not just the cosmic hum, not just the magnetic mysteries and plasma physics that will keep scientists busy for decades. It found that we are brave enough to go there. And that is perhaps the most important discovery of all. When Voyager was launched in 1977, the average person expected to live about 70 years. The Cold War divided the world into hostile camps. The most powerful computers occupied entire rooms. The internet did not exist. The world was smaller, slower, more limited. And yet, in that world, we built a spacecraft and launched it toward the stars. We knew it would take decades to reach the edge of the solar system. We knew we might not live to see its greatest discoveries. We sent it anyway, because we believed that some things matter more than our individual lifespans. That spacecraft is still out there, still traveling, still carrying our message into the cosmic void. It has crossed every boundary we feared might stop it. It has measured every environment we thought might destroy it. It has proven that the universe, though vast and strange and sometimes terrifying, is not closed to us. The wall of fire burns at the edge of the solar system. But Voyager passed through it and found the stars waiting on the other side. They are still waiting. And someday, we will follow.